transform. Okay, so we have studied how to find the Laplace transform and how to find the inverse Laplace transform. Actually, we studied Laplace transform for a purpose. So what is the purpose? Simplifying using the Laplace transform. Many problems can be simplified and solved easily. Okay, so now only we are going to look at the application of Laplace transform. Okay, applications of Laplace transform. So there are several applications. So we'll look at one by one. In this course, I would like to cover these four applications. One is evaluating certain integrals. So some definite integral, we can use Laplace transform. Similarly, to solve ordinary differential equations, maybe it's a constant coefficient or simultaneous differential equations or even variable coefficients. So in this course, actually, I'm not going to cover this part, but in the lecture note it is there, but I'm not going to discuss this in this class because we have to start Fourier transform as well, so we don't have enough time. Therefore, I'm not going to cover the variable coefficient method, but the notes is given in the handout, so you can refer and try to understand. But the thing is, in the examination, I will not going to take question from that section. I will not take. Okay, so you don't need to worry about that. If you are interested in that, you can just refer the notes and try to understand. Or if you have any doubts on that, you can come and ask me when you come physically. So that is our second one. Third one, solving PDEs. And the fourth one, solving integral equations. So sometimes we call this as a integral differential equations. Okay. So we are going to look at these four applications today. And hopefully I will finish this handout today itself. And in the next class, we can start Fourier transform idea. Okay. So I think today I will be able to finish this handout number 4. Okay. So if you don't understand anything, anytime you can ask me. Anytime you can stop me and ask questions if you don't understand. But since already we have studied finding Laplace transform and inverse Laplace transform, actually application is nothing. So if you are thorough in finding Laplace transform and inverse Laplace transform, application is nothing. The application is just you take the Laplace transform and then you take the inverse Laplace transform and you find the solution for that one. Therefore, so here, so the general thing is, this is your problem. Okay, so this is your problem. Now you take Laplace transform this to problem. This is your problem P. Okay, this is your problem P. Now you take Laplace transform this to P. Now if you take Laplace transform this to problem, okay, now you will get say inverse of this one. So you will get inverse of this one. Say that means that you will get this one, inverse of this one, inverse of this one. Then if you take the inverse of this one, okay, then you can get the original problem. So that is the idea. So if we first take the Laplace take Laplace operation both sides, and then we convert that equation, and then we take inverse Laplace, and then we get the solution for the original problem. So you can understand this process easily, no problem. Okay, so don't worry about that. We'll discuss one by one. So first one, evaluating integrals. So first application, as the first application, we are going to evaluate some integrals. In some cases, we simply recognize the given integral as a special case of Laplace transform. So actually, using Laplace transform, we cannot evaluate each and every integration. We can evaluate only special case, special integration, special types of integration. Okay. So one of the examples here. So let's read it, please. In some cases, we simply recognize the given integral as a special case of integral transfer for a particular value of transformable variable s. Okay, for a transformable variable s. In such case, we get the answer by plugging the values of s to the transform function. So you will understand what is this. Okay. Now we have to evaluate this one. Okay. We have to evaluate this one. Okay. So if you look at this one, this is somewhat, if you look at the limit 0 to infinity, here we have e to the power minus 2b. So it is somewhat, if you carefully observe this one, okay, this looks like, somewhat Laplace transform form, isn't it? Laplace transform form. What is the Laplace transform form? 0 to infinity e to the power minus st into capital F e. So this is the Laplace transform of ft, isn't it? This is the Laplace transform of the function ft. Okay. So you notice here, if you take your ft as 2 into cos t, and if you take your s as minus 2, then actually it is same as Laplace transform of t cos t, isn't it? Therefore, we can use Laplace transform because this integral actually looks like this form. It looks like this form. Therefore, we can use this. We can use Laplace transform to find the integration of this one. So look at here. So we want to find the integration 0 to infinity t into e to the power minus 2t cos t into t. This is what we want to find. Now, instead of finding this one, what I'm going to do is I'm going to find the Laplace transform of Laplace transform of t into cos t. So t into cos t is what actually? What is the Laplace transform of t into cos t? Can anyone tell me what is the Laplace transform of t into cos t? What is the Laplace transform of t into cos t? So first of all, tell me what is the Laplace transform of cos t? What is the Laplace transform of cos t? Can anyone tell me what is the Laplace transform of cos t? You have to speak, otherwise, it will be difficult for me to continue this class. What is the Laplace transform of cos t? Cos t is equal to s over s square plus 1. S over, yeah, good. S over s square plus 1. S over s square plus 1. Now, if Laplace transform of cos t is equal to s over s square plus 1, what is the Laplace transform of t into cos t? Multiplication property. Multiplication by t to the power n. What is the Laplace transform of this one? Multiplication property. So multiplication property says what? How to find the multiplication property? Using the multiplication property, you can see. Please respond to my question. Using the multiplication property, yeah, minus 1 df s into ds, isn't it? So that is, so if you have a function like this, Laplace transform of e to the power n into ft, so this is equal to minus 1 to the power n into ds DFS DSN. Okay. So here the value of t is 1. Therefore, this is nothing but t of s square plus 1 into minus 1 to the power 1. Minus 1 to the power 1. So if you differentiate this one, minus 1 into, okay, so 2s, sorry, if you differentiate this one, this comes as s square plus 1 minus s into 2s divided by s square plus 1 all units. Okay, so if you simplify this, you will get s squared minus 1 over s squared plus 1 whole units. Okay, square plus 1, square plus 1 over this one, square plus 1. So yeah, sorry, it should be minus 1. There's a minus. Square minus 1 over square plus 1. Okay. So square minus 1 over square plus 1. So now, what is the Laplace transform of t into cos t? Actually, what does it mean actually? This is actually 0 to infinity e to the power minus st into t into cos t. So this is equal to s squared minus 1 over s squared plus 1. But now if you look at the integration that we want to find, instead of s in this one, now if you look at only this one, instead of s, if you put s equal to, then that is the integration that we are asked, isn't it? So putting s equal to we get 0 to infinity t into e to the power minus 2t into cos t dt equal to, if we put s equal to in the right hand side, we will get 4 minus 1 over 4 plus 1 all this here. So which is equal to 0 over 25. You understand this? You understand? So this is one of the application. If you understand, tell me whether I understand or not.
Yes, sir.
Right. So now I have put some exercises here. So please try this one. And shall we do the second one? Shall we try the second one? So the second one is homework problem. So integration 0 to infinity. We want to find out e to the power minus t sin square t over t. Sin square, sorry. So e to the power minus t sin square t over t. This is what we want to find. So if you look at this integration, You can, if you match with the Laplace transform, we have e to the power minus t something, isn't it? Then we can match with Laplace transform operator, isn't it? You can match with Laplace transform. Therefore, let's try to find the Laplace transform of, first of all, we'll find Laplace transform of sin square t. Sin squared t over t. Then in this value, once you find this one, if you put t equal s equal minus 1, sorry, s equal 1, because instead of s, what you have? Minus t. So if you put s equal 1, then you can get the answer easily. So how to find the Laplace transform for this one? So we have squared here. We have squared here. So if you have squared, what you can do? If you have squared, then this is same as Laplace transform of what? So you have to express first 2t, no? So first 2t is equal to 1 minus 2 sin squared t, isn't it? Therefore, you can write this as 1 minus first 2t over 2 divided by 2t. Okay. So this is equal to Laplace transform half 1 over t 1 over t minus half Laplace transform of first 2t by t. So can you tell me the answer of this one? Half into what is the Laplace transform 1 over t. So you can use the property dividing by t property. So if you have something, if you have Laplace transform of ft over t, what is the answer of this one? Can anyone tell me what is the answer of this one? What is the Laplace transform of ft over t? Ft over t is what? If ft is equal to fs, ft over t is equal to what? Please tell me. You all know everything. We have studied all these things. If you don't know, then it's difficult. Please tell me what is the Laplace transform of ft over t?
Integration s to infinity
s to infinity
fu du.
fu du. Okay. Integration s to infinity fu du. Okay. So here, what is the Laplace transform 1 over t? Can anyone tell me what is the Laplace transform 1 over t? So that is integration. Okay. So that means that your ft here, your ft is 1, no? So this is your ft. So fs is what? What is the Laplace transform of fs? That is 1 over s, but we are writing the function in u. Therefore, this is 1 over u. 1 over where s varies from 0 to 0. Okay. S varies from 0 to minus half times this is actually integration 0 to infinity fu. So that is s over s squared plus s over s squared plus, sorry, instead of s we have to put u, no? So we want to put u over u squared plus o. So if you simplify this, we do the integration of this one, we get half ln u. So we have to substitute s to infinity, okay, minus half, okay, half. And what is the integration of this one? What is the integration of this one? Can anyone tell me the integration of this one? U over u squared plus 4. What is the integration? So if you look at here, to differentiate the denominator, it is there. Therefore, this is ln mod. You don't have 2 here. Therefore, this will be 4. 4 ln u squared plus 4. Squared plus 4. Where s tends to infinity. Now, you can write this as, so you can, if you take the limit as common, you can write this as ln u, okay, divided by, so here minus 1, so minus mean you can write this one, so, no? So divided by 2, here you can put u squared plus 4 the power 1. You want to substitute, you want to substitute st. So what is the answer of this one? Can anyone tell me what is the answer of this one? So what is the answer of this one? ln. So you can write this as so if you take half out, you can write it as half. You can write it as half u over square root of u squared plus 4. Okay, we can write this one. We have to substitute st. So can you tell me the answer of this one? So when you substitute s, when s tends to infinity, what is the answer? So half into limit u tends to infinity, u over square root of square plus 4 minus, if you substitute s, then you will get ln, sorry, here so this is equal to, I'm writing this way, is equal to half into limit u tends to infinity ln u over u squared plus 4 minus, you put s ln s over square root of s squared plus. So when n tends to infinity, what is the value of this one? When n tends to infinity, what is the value of this one? If you divide u up and down, then this becomes half limit u tends to infinity. You can say ln 1 over 1 plus 4 over u square. Minus ln s over square root of square plus 4. So when n tends to infinity, what is the answer of this one? This is half into, this is a, when u tends to infinity, this is ln 1 minus ln s over square root of s square plus 1. Okay, so ln 1 is what? It is 0, no? So we get minus half time ln s over square root of s square plus 1. So s square plus 4, no? I'm sorry, it should be 4. But now if you look at your integration, actually the value of s is what? Can anyone tell me value of s? What is the value of s here? Can anyone tell me the value of s here?
1.
Yeah, 1. So if you put s equal 1 here, so put s equal 1, we get integration 0 to infinity e to the power minus t sin square t over t equal to minus half times ln ln what? ln 1 over square root of 5. So minus ln 1 over square root of 5. So this is equal to what? This is equal to, if this is minus, no, so you can write it this as half times ln, without minus you can write it as square root of 5. So this is equal to, you can take 1 over half out, so that is equal to 1 over 4 into. Because you know this, no? ln a to the power n is equal to n into ln a. Okay. So using that result, you can take this one. Do you understand this?
Yes, sir.
Do you understand? Anybody have any problem in here? So evaluating this one, it's a limit. Okay, so I will send this to you. I will send this not writing pad to you, so you can understand it if you want. So you have to, so appropriately choosing the value of s, we can evaluate certain integral. Okay. So I think you can try the first question. This is a homework question. Please try this. So this is actually first application. The first application is actually evaluating certain integrals. So we are done with this. Now we'll talk about solving ordinary differential equation. So in this class, I'm going to discuss two types of ordinary differential equation. One is the constant coefficient and simultaneous equation. I'm not going to discuss this one, but in the handout, you can find the notes for this also. If you are interested, you can read it and try to understand, but I will not take any question from this section for your assessment or final exam. Okay, so let's forget about this one. Right, so constant coefficient mean what? All the constant coefficients are constant. So look at an example here. So later you will understand what is it. Here they are explaining the but I will explain. We are going to discuss now. Y double dash t plus 2y dash t plus yt equal to 3 times t into e to the power minus t, and initial condition is important. Okay, so we are going to solve this differential equation, ordinary differential equation with initial condition. If it is a second order differential equation, then y0 and y dash 0 should be given. Otherwise, we cannot solve this equation using Laplace transform. Okay, so this is the problem that we are going to discuss. I am going to explain this. Y double dash t plus 2y dash t plus yt equal to 3t e to the power minus 3t. Okay, so now we are going to discuss the second application, solving ODEs. We are going to discuss solving ODEs. So solving ODEs, so example, we can try to understand the procedure, how we can use Laplace transform to solve this one. So the problem is y double dash t plus 2y dash t. I think they have written capital letters. I'm using a simple letter. Okay, and yt, sometimes t will not be mentioned. Okay, yt equal to what is the question? 3t e to the power minus t. So 3t e to the power minus t. So first step, okay, take Laplace transform. This is the procedure. This is the common procedure for any question. This is the common procedure for any question. The first step is, so I will write step one by one. So step one, take Laplace both sides. Take Laplace both sides. Step number two, solve the algebraic equation. Now, once you take the Laplace transform both sides, you will get an algebraic equation. Solve the or simplify the algebraic equation. Simplify the algebraic equation. Step number three, take inverse Laplace. Very simple. There are only three steps. First one, take Laplace operator both sides. Then simplify the algebraic equations, and take inverse Laplace transform. So this, if you do these three steps, you can easily get the solution for this differential equation. So first of all, we have to say one thing, that is, let the Laplace transform of function yt equal to, we will say ys. Okay, here, look at here, one important thing. Here, the variable is given in t. Okay, variable is t. Sometimes the variable may be x. Then no problem. You can say Laplace transform yx. Instead of t, you can have x, no problem. But here, this variable can be s, no problem. Okay. The given equation is in x, no problem. You can write it as Laplace transform of yx is equal to, you can write it as Laplace transform of y of x is equal to, you can take it as ys. Okay. So here they have given in t directly, so therefore we don't want this one. Okay, we don't want this one. So now we are taking Laplace transform yt equal to ys. From both sides. So transform both sides. Then we have y double dash t plus 2. This is step number one. Huh? This step. Now I am doing step number one. Laplace transform of y double dash t plus Laplace transform of y dash t plus Laplace transform of equal to Laplace transform of dt into e to the power minus t. That is the question, no? Yes, that is the question. E to the power t into minus 3. E to the power t into minus 3. Now, using the linearity property, you can write this, no? Laplace transform of y double dash plus 2 times Laplace transform of y dash plus Laplace transform of y equal to Laplace transform of dt into e to the power minus t. So, can anyone tell me what is the Laplace transform y dash y double dash? Here, see, we have taken Laplace transform yt as ys. Okay. So, can anyone tell me the Laplace transform y dash t? If you remember, if you correctly remember, can you tell me? What is the Laplace transform? What is the Laplace transform derivative? Laplace transform of f dash t is what? We know that this is equal to s into fs minus capital F. What is the Laplace transform of f double dash t? We know that this is equal to s square fs minus what? Can anyone tell me? S into f0 minus capital F dash. Am I correct? Am I correct or wrong? Please tell me. These two are correct or not? Please tell me using the derivative. So Laplace transform of derivative. What is the Laplace transform of first derivative? S into fs minus f dash 0. What is the Laplace transform of second derivative? S squared fs minus sf0 minus f dash 0. Am I correct or wrong?
Correct, sir.
Correct, sir.
Yeah, correct. No, it's correct. So using the same thing, here I have the second derivative. Since I have the second derivative, I can write this as s squared into y of s, because I have taken Laplace transform of yt as Laplace transform of yt as ys. Therefore, I can put it ys s into sorry, I must put capital, otherwise we will get confused. I'm sorry for that. Sorry. So, let me put it as capital Y, otherwise you will get confused. Sorry for that. Capital Y, capital Y, capital Y. Okay, so let me take this as capital Y. So Laplace transform of capital Y is equal to simple ys. Yeah? Simple ys. Therefore, here is my capital Y. This changes as capital Y. I'm sorry for that. So Laplace transform of capital Y double dash t. Here notation is very important, otherwise you will get confused. Plus 2 capital Y dash t plus capital YT equal to Laplace transform of capital Y double dash T plus 2 times Laplace transform of capital YT Y dash, no? Plus Laplace transform of capital YT. So capital, we have taken Laplace transform capital YT equal to simple ys. Simple ys. Okay, like Laplace transform of capital Ft equal to simple Fs. We are taking Laplace transform of capital YT equal to simple ys. Therefore, using this derivative property, you can write this as squared into ys minus capital Y0, sorry, minus s into, this is capital Y0, by capital Y0, look at here, SFS, S squared Fs minus S into capital F0 minus capital F dash 0. Okay, so you have to carefully look at this one. Here it is what? F dash T into S into F0 minus capital F0. Therefore, this is simple ys, this is capital Ys minus capital Y dash 0. Capital Y dash 0. So this is the Laplace transform of this one plus 2 times Laplace transform of this one. So that is S into Fs. Fs is ys here minus capital Y0 plus Laplace transform of capital T, that is nothing but simple ys, equal to Laplace transform of 3t into e to the power minus t. Can anyone tell me the answer of this one? What is the Laplace transform right hand side? 3t into e to the power minus t. So that is 3 into, what is the Laplace transform of t? Then multiplication by e to the power 8. That's all. So can anyone tell me the Laplace transform of 3t into e to the power minus t? Can anyone text me the answer of this one? What is the Laplace transform of this one? N is equal to 1. So we have that Laplace transform of t to the power n. T to the power n is what? Laplace transform of t to the power n is what? N factorial over Sn plus 1. So n is equal to 1. Therefore, this is S squared. But here we have minus 1. So Laplace transform of e to the power 18 to ft equal to f of s minus a. Is it? Therefore, s minus a. Therefore, here value of n is 1. Therefore, we will get s squared, but minus 1. So this is equal to 1 over s minus 1 whole square. Am I correct? Am I correct?
Yes, sir.
Is this correct?
Yes, sir.
Okay, fine. Yeah, that is correct. But that is wrong, no? It should be minus 1, no? So here what we have is minus t, no? Therefore, this should be plus. Why this should be plus? Because our a is here minus 1. Our a is minus 1. Therefore, if this is minus 80, then this will be plus a. Okay, therefore, we'll get this one. Now, it's a time to do the substitution for initial value. So if you look at the initial value of this system of this ordinary differential equation, it says that y0 equal to 4, y dash 0 equal to 2. So it says that y0 equal 4. So capital Y0 equal 4 and y dash 0 equal to, what is that value? 2, no? So y dash 2 is equal to 2. Now if you substitute this value here, you will get s square, okay, simple ys minus s into y0 equal to 4, no? So this is 4s minus y dash 0 equal to 2. So 2, that is first part, plus 2 into sys is equal to sys, there is no change in that, minus y0 equal to 4 plus ys is equal to 3 over 3 over s plus 1 all whole square. Now you take ys as subject. Here you have ys, here you have ys, here you have ys, and send everything to other side. So if you take ys as a common factor, okay, so let's try this one. So you can write it as square plus 2s plus 1. That is that they are the coefficient of ys. And if you send rest of the thing, we'll have 3s plus 1 all in square. Here you have plus 4s. When this goes to this side, you have plus 4s. This is minus 2. This is minus 8. Therefore, this becomes plus 10. This becomes plus 10. Okay, this becomes plus 10. So now we'll go to this handout. You see, we are having this one. So actually, we are having this one. Yes. So you can write this as what? This is what? S square plus 2s plus 1 is what? S plus 1 all in square into ys is equal to p over s plus 1 all in square plus 4s over 10. Isn't it? 4s over 10. So you can say that ys is equal to, ys is equal to, we have p over s plus 1 all in 4, because when you divide by this s square, this becomes 4 plus 4s plus 10 divided by s plus 1 all in square. Okay. Now actually, by solving this differential equation mean what actually? So solving this differential equation mean what actually? We have to find capital YT. Isn't it? So question is, what is capital YT? What is the capital YT? That is the question. Solving this differential equation mean what? We want to find out our capital YT. So now here, if you look at here, we have taken, so here we have taken as what? Laplace transform of capital T equal to simple ys. Now we have found that this is our simple ys. So if we take inverse Laplace transform of ys, we take inverse Laplace transform of ys, then that will automatically give you what? Capital YT. This is what you are asked to find. By solving this differential equation, what we are trying to find? By solving this differential equation, what we are trying to find? We are trying to find YT, capital YT, the function YT, isn't it? Capital YT. So now what we have done, we have taken Laplace transform both sides and we have simplified it, and we are using the applying the initial condition here, and we are getting this equation. Okay. Then what we can do, we want to, so if we take the inverse Laplace transform of ys, that will be equal to our capital Y2. So this is what we want. This is what we want actually. Therefore, now we have what ys is equal to this one, and now we are going to find, we are going to take an inverse Laplace transform. So to take it, before we taking the inverse Laplace transform, we are writing this Laplace transform in a different form. So why we want, so that we can easily write the inverse Laplace transform. So can anyone tell me what is the inverse Laplace transform of this one? And here you can write this as this way, using the partial fraction. You can write this one. So this part is actually we are using the partial fraction. We are using the partial fraction. So using the partial fraction, you can write this way. Okay, 4 over s plus 1, 6 over s square plus 1. Okay, so what is the inverse Laplace transform? 3 over s plus 1 whole in 4. So what is the inverse Laplace transform? 3 over s plus 1 whole in 4. What is this? Actually, we have to use change of scale property. We have to use change of scale property. So this is equal to actually 3 into e to the power. So when you have plus 1 to the power 4, so that is nothing but what? So normally we know that. So you have to study well, otherwise it will be difficult. Huh? So look at here. So if you have a Laplace transform of ft, capital Ft, equal to Fs. Okay. So Laplace transform of e to the power 18 to capital Ft, we know that f of s minus t. So now what we have is Laplace transform of, we know that t to the power n equal to t to the power n is equal to what? N factorial over s to the power n plus 1. Okay. So now what we have is Laplace transform of, we want to find out this one. Here we have 1 over s to the power 4. So 1 over s to the power 4 mean what actually? So what will be that? So value of n is equal to 3. Therefore, this will be e to the power 3. But here we should have n factorial, that means 3 factorial. But we have 1 only. Therefore, this is divided by 3 factorial. So, e to the power 3 over 3 factorial Laplace transform e to the power 3 over 3 factorial is actually equal to 1 over s to the power 4. So now if you multiply this with, e to the power minus t into e to the power 3 factorial in what? 1 over s minus a, isn't it? When it is multiplied with e to the power 8, we get s minus a. So here we are having minus 1. Therefore, we are having s minus minus 1. The power, isn't it? So that is equal to 1 over s plus 1 to the power 4. Therefore, if you have in this form, it is actually same as multiplying by e to the power minus t. So that is what happening here. That is what happening here. So here they are having 3 out and they are multiplying 3 into e to the power minus t, and it is same as finding Laplace transform of s to the power 4. Here there is no any difficult thing here. This is nothing but Laplace transform of we know that e to the power at equal to 1 over s minus a. So if you put a equal minus 1, we get s plus 1. So that is the Laplace transform of this one. Similar to this one, we can take here. Here it is 4. Here it is also minus 1. Therefore, we are multiplying by minus 1 to this one. Then once you get the Laplace transform of this one, we are getting the final answer is this one. So this is our capital Y. Capital Y is this one. So now we are able to solve this equation. Okay. So this is how we have to do this one. Do you understand this one?
Yes, sir.
Right. So if you understand this, we'll try this question. We'll try this question. So y double dash t plus y dash t equal to 0, y0 equal 1, y dash 0 equal 0. So exercise number 2. We have capital Y. Yeah? So you have to write the capital and small carefully because you are using small y for Laplace transform. Therefore, y double dash t plus capital Y dash t. No? The capital Y dash t equals 0, y0 equal 1, y dash 0 equals 0. Capital Y dash t equal 0 subject to the initial condition y0 equal 0, y dash 0 equal 1. So other way, no? I'm sorry. So this is 1. So what we have to do? What is the first step? Can anyone tell me what is the first step? Can anyone tell me what is the first step? Can anyone tell me what is the first step of doing this question?
Take two side Lagrange.
Yeah, we take Laplace transform both sides. So if we take Laplace transform both sides, so before that we have to say let, we have to write let, you have to write this one, okay? Laplace transform of capital YT equal to simple ys. Now take Laplace transform both sides. Laplace transform both sides. So if you take Laplace transform both sides, that is Laplace transform of capital Y double dash t plus y dash t equal to Laplace transform of 0. Fortunately, right hand side we have 0. So if you take the Laplace transform of so using the linearity property, you can always write this as Laplace transform of y double dash t plus Laplace transform of capital Y dash t equal to Laplace transform of 0. Okay, so you can write this one as square simple ys minus s into, can anyone tell me what is the value here? S into what?
Capital Y0.
Very good. Capital Y0 minus, any other one can tell what is what? Minus
Y dash of 0.
y dash 0. Is that capital or small?
Capital.
Capital. Good. So that is y dash 0 plus plus another one can tell what is the Laplace transform y dash 0. Another one can tell what is the Laplace transform this one. What is the Laplace transform y dash 2? Any other one can tell me? Ladies? One of you? Please tell me, I'm waiting for your response. What is the Laplace transform y dash t? If you are able to tell y double dash t, then you can, it is easy, no, y dash t. Tell me what is the Laplace transform y dash t?
S into small y of s
Very good. Small y of s
minus
minus
capital Y dash of 0.
capital
Y0.
Y dash 0.
not y dash. It's
Y0.
y0, no?
Y0.
It's y0 equal to Laplace transform of 0 is anyway 0. But already we are given initial condition that y0 equal to 1, y dash 0 equal to 0. So if you substitute that also here, we get a square ys. This one is 1, therefore minus s into 1 minus this is 0 plus s into ys minus this is 1 equal to 0. What we have to do next? What we have to do next? Anyone tell me what we have to do next? We have to, huh? What we have to do? Tell me. What we have to do? We have to make ys subject, isn't it? So we have to take ys. We find ys in terms of other. So if you take ys, then you have here s squared plus s. And if you bring rest of the thing to the other side, we'll get s plus 1. We'll get s plus 1 because this is s, this is 1, so that goes to that side. So if you make ys subject, so ys is equal to s plus 1 over, if you take s, then that comes as s plus 1. So if you simplify this, we get ys is equal to 1 over x. So we get ys is equal to 1 over x. Is that over? Now what we have to do? What is the next step? What is the next step?
Inverse Laplace.
Yeah, we have to take the inverse Laplace for this one. Inverse Laplace of simple ys. So if we take inverse Laplace of simple oneness, what is the answer? What is the Laplace, inverse Laplace of 1 over s? Can tell me what is the answer of this one? 1 over s. What is the inverse Laplace of 1 over s?
1.
1. So that is 1. Therefore, our function yt, capital Yt, equal to 1. So that is the solution for this equation. Capital Yt equal to 1. It's a constant function. It's a constant function. No problem. We can get the answer 1. Okay. So if I haven't made any mistake, this is the correct answer. Do you understand? Is it easy, no? This is easy, no? Do you understand this, no?
Yes, sir.
Right, fine. So I don't know whether I made any mistake anywhere. Please check this one. Huh? Please check this one. So we are taking this one. So this is correct. This is good. The answer, but it is satisfying the equation. No? Double dash 0 plus this one is 0. Y0 equal to 1. Y0. If you put this is a yt, no? So if you put c, if you put y0, we are getting 1. Okay. If you differentiate y dash t, it is 0. So if you put y dash 0, it is 0. Also y dash t is 0, y double dash t is also t 0. Sorry, this all are capital. I'm sorry. Y double dash. So y double dash t plus y dash t is equal to 0. So it is satisfying the equation. Look at here, y double dash t plus y dash t equal to 0. So our satisfying equation as well as initial condition. Therefore, this is the correct answer. So this is the correct answer. So you understand? Similar. So this is nothing but we are using the differential operator. So this is nothing but same. So better use capital, no problem. Okay, make this capital. Make this capital, please. So otherwise, if it is simple y, you can say that Laplace transform of simple yt. You can say that is equal to fs. Then business is over. So always you don't need to take capital Y, simple y. If it is simple y, you can say it is simple fs. Simple fs, no problem. Then business is over. So don't worry about the variable given. The variable is given in x, no problem. You take it Laplace transform of simple yx equal to ws. So finally, when you have to give the answer, you have to give in x because our variable is x here. The previous case, our variable is t. That is why we gave our answer in t. Look at here, answer in t. The previous example, we gave answer in t here. Look at here, final answer we gave in t. Okay, so depends the variable, we can answer. Do you understand, no? You understand this? Tell me whether you understand or not.
Yes, sir.
Right, fine. So now we are going to solve ODs, simultaneous ODs with constant coefficient. So here, why we are saying constant coefficient? So if you look at the coefficient here, it is 1, it is 1, it is 2, it is 5, it is -3. So if you look at the coefficients of these ODs, they are constant. So this method actually, the method that we studied actually applicable for only constant coefficient. So later we can see there is another method for variable coefficients. Okay, so actually I will not cover this. I will not take this for your exam. So don't worry about that one. Okay. Right. So now we are going to solve simultaneous equation ODs, simultaneous ODs. That means you have two functions. We have functions xt, capital XT, and capital YT. So we are given two differential equations together. Okay, so this is the format of the equation. For an example, this is the equation we are having. So here, by solving this equation, we have to find what is our capital XT, what is our capital XT, and what is our capital XT. So by solving this simultaneous ODE, we have to find two functions. Here actually we have only one function YT. Here we have two functions xt and yt because we are having simultaneous equation here. Okay, so here the initial conditions are given. Why the initial condition x dash 0 is not given? Why? Can anyone tell me why it is not given? Why dash 0 is not given? Why? In this problem, these two are not given. Why? Why they are not given? Can anyone tell me why they are not given? Say here y0 is given, y dash 0 is given, but here x0 and y0 are only given. X dash 0, y dash 0 not given. Why? Can anyone tell me why it is? Why it is?
It is not second derivative.
Yeah, that's good. That's the answer because here this equation, if you look at this equation, it involves only first derivative. So if you look at the first different Laplace transform first derivative, we don't want these things. We don't want these things. Therefore, they have given only these two. Okay, that's the correct answer. Now, same as earlier one, there is no any difference. But only thing is what we are doing here is we are taking Laplace transform of capital Xt as simple xs, and Laplace transform of capital T yt we are taking as simple ys. That's all we are doing. So here, if you look at your first function x dash t, so here x dash t equal to 2xt minus 3yt the capital yt. Next one, y dash t equal to minus 2xt plus y. Y dash t, capital Y dash t is equal to minus 2xt plus y. Minus 2xt plus y. So now we want to solve this equation. So we are taking let. So you have to write this one. Otherwise, the examiner will not know what is your xx and ys. Okay. So let Laplace transform of capital Xt equal to simple xs, and Laplace transform of capital Yt equal to simple ys. Therefore, now if we take Laplace both sides, the first side, now here we have x dash t, so we'll have s into simple xs minus, can anyone tell me what will come here? Can anyone tell me what will come here if you take the Laplace of the first equation, x dash t sx into
capital X no. Capital X no.
capital X
0.
0, very good. Capital X 0 equal to, here if you take the Laplace transform right side, then that will become 2sx minus, sorry, function is 3ys. Similarly, if you take Laplace transform of the second equation, if you take Laplace transform, that will become s into ys minus capital Y0 equal to, equation is minus 2xt, therefore minus 2xs plus yt, therefore that is ys. So now we have two equations. So in the question, we are given that x0 equal to 8, y0 equal to 3. So that we are given. So we are given that x0 equal to 8 and y0 equal to 3. So we have, if we apply the initial condition, we'll get s into, so if we bring xs to one side, then you will have s minus 2 xs and 3ys. So this come plus 3ys equal to y0 equal to 8. Sorry, x0 equal to 8. So that is minus x0. When it goes to this side, it becomes plus 8. So this is our equation number 1. Second equation, if you take ys common, so that will come s minus 1 into, okay, we'll write xx first. So if you write sx first, then that will come as minus 2 we have. So when it comes to this side, we'll have plus 2sx plus, and if you take y s minus 1 ys is equal to your y0 is equal to 3. Therefore, when it goes to this side, we have 3. So now we have a simultaneous equation in Sx and Ys. So if we solve this one, simply what you can do. So if you divide this first equation by this one and subtract from this one, you can have 3 over s minus 2. Yeah, 3 minus. Sorry, let me write this. So if you subtract this one and dividing by that one, so we'll get 3 over s minus this one minus s minus 1 over 2 into ys is equal to 8 over s minus 2 minus 3 by 2. So similarly, you can find out ys. So here, let's without writing this, it takes time. So here we are getting the things. Look at here. So we are getting the same equation here. So then we are solving. When we solve, we are finding x and y. So here, instead of x's, we are writing x. Instead of ys, we are writing y. That's all. Okay. So no, don't worry. Don't confuse here. So here x's, y, we are just writing x. Ys, we are writing y. So these are two simultaneous equations in x and y. So we are solving this simultaneous equation. You know how to solve this simultaneous equation. Very simple. It's a grade 5 work. So if you solve this one, this is the answer you get for Sx. And this is the answer you get for Ys. So now we want to find capital XT. So how to find capital XT? So we have to take the inverse for simple x's. Isn't it? So if you take inverse for this one, what is the answer of this one? This is nothing but 3 into e to the power 40, no? Plus this is nothing but 5 into e to the power minus. Here similarly, if you take the Laplace transform of ys, so this is nothing but 5 into e to the power minus t. This is nothing but plus 2 into e to the power minus 40. Sorry, minus 40, plus 40, yeah? I'm sorry, plus 40. So we are getting the answer. So finally, we are getting this answer. So here we are calculating capital XT and XY. Do you understand this? Do you understand this, friends?
Yes, sir.
Right, so that's fine. So I'm not going to discuss this one. Here we are discussing a special type of variable coefficient. Special type of mean when you have the variable in this form, t to the power m form. Okay, we are not discussing any other different form. Okay, so this is very simple because why? We have studied what will happen if. So this is actually you can use multiplication by t property. Multiplication by t to the power n property, and you can solve this equation. So if you have time, please look at please try to go through this and try to understand. But definitely, I will not have this the optional. Okay, I will not have it for this one for the exam. Okay, right. So I'm just skipping this part. But if you just go through this one, you can easily understand. Same as earlier. You know, when it is multiplied by t to the power m, we know the Laplace transform, how to find the Laplace transform. Then you just do the same as earlier and you find out this one. Okay, so you can do this one. Now we are moving to the final one, that is solving PDEs. Okay, so I think so I think tomorrow, not tomorrow, in the next class, I will discuss solving PDEs. Okay, solving PDEs. Now I go to 3.4 because we have half an hour only. Therefore, it may take more than half an hour. If we start to discuss solving PDEs, it may take more than half an hour. Okay, it may take more than half an hour. But definitely, in your final exam, you will get one question from solving PDEs. Definitely you will get one question from this part. Okay. Okay, not definitely, but sometime I will tell you before the examination. Okay, I will tell you before the examination which application will come. Okay, which application part will come. Okay, definitely one of the thing that we discussed will come for your exam. Okay, so sometime if you look at the last past paper, solving PDK. Okay, so now I skip this for next class. Okay, I just keep this for next class and we'll go to the last part, that is 3.4. Okay. So I'm going to talk about integral equation, solving integral equation today and finish the lecture today. Okay, so only one part is missing, so that I will cover in the next class. Okay, that I will cover in the next class. Okay, I will tell when. So this is the general form of integral equation. So what do you mean by integral equation? This is the general form of an integral equation. Ft equal to gt plus lambda a to b ktu plus fu. This is the general form of integral equation. Okay, this is the general form of integral equation. Why we are saying integral equation? Because this equation involves integration. Okay, here if you look at this one, the function gt non-function. It's a non-function. Function ktu, it's a non-function. But what we have to do is we have to find out ft. So by solving this integral equation, actually our task is to find ft. Okay, these two are non-function. Okay, these two are non-function. Okay, so here look at here. This is the general form of a differential integral equation. The function gt and ktu are non. Okay, ft is to be determined, so we have to find ft. So our task here is to find ft. By solving this integral equation, our task is to find ft. Okay, here kt is called kernel of the integral equation. In Laplace also we are saying e to the power minus s is the kernel, isn't it? Likewise, in this integral equation, this part we call it as the kernel of the equation. Kernel of the equation. The upper limit b may be either variable or constant. Okay, look at here. Here this upper limit in this integral, this may be a variable. This may be a variable or this may be a constant. Okay, this may be a variable or constant. Okay, if a and b are constant, so if a and b are constant, then this equation is called Fred-Hoyle integral equation. Okay, this is special integral equation. If a and b are constant value, then such integral equation we call it as the Fred-Hoyle integral equation. This is the name of a person. Okay, if a is a constant while b equal to t. Okay, so in this case, a is always constant. A is always constant. Okay, this is always constant. A is always constant. If b is constant, then we call this as a Fred-Hoyle equation. If b equal to t, look at here, the same t. Here b equal to t, such equation we call it as the Volterra integral equation. We call it as a Volterra integral equation. Okay, Volterra integral equation. Then another thing, look at this one. If ktu, the kernel of the integral equation is of this form, ktu minus form. Okay, look at this one. If the kernel of the integral equation is of this form, ktu minus u form, then it is called convolution type. Integral equation is convolution type. Integral equation is convolution type. Okay, integral equation we call it as the convolution type. So look at here. This is the general form of the integral equation. General form is capital Ft equal to gt plus a to b k t comma u into fu t. Now in this equation, our task is to task. By solving this equation, our task is to find capital F. That is the question. By solving this equation, we want to find capital FT. Look at here. This is capital FT. This is capital FU. Same. These two are same. Look at here. These two are same. Okay. So here GT, comma KT, comma U. No. Not mean we know they are given functions. They are given functions. They are not. Okay. Here KTU we call it as the kernel. KT we call it as the kernel. Okay. A always constant. B, there are two possibilities. One is the variable. That means T or constant. If it is constant, we call this as Fred-Hollom equation. The special name we are giving. If it is variable, we call this as a Volterra equation. Finally, if KTU, the kernel of the function is of the form KT minus U, then we say the integral equation is convolution type. You can remember in the last class we studied convolution theorem. We call it as convolution type. So can you tell me the convolution theorem? What does it say for Laplace transform? Say for an example, inverse Laplace transform of Fs into Gs equal to 0 to E capital Ft into Gt, you know. So this is actually called the convolution theorem. Laplace transform of Fs into Gs is equal to 0 to T Ft Gt minus U into dU. Okay, so from this one, you can rewrite this as Laplace transform of integration 0 to T Ft Gt minus dU. This is nothing but what? Inverse. So this is Laplace transform is what? Fs into Gs. So from this one you can write this. So here if like inverse Laplace transform of Fs into Gs is this one, Laplace transform of this one is what? Fs into Gs. So look at here. This is actually a similar thing you can find out in your integral equation. Okay, so if you look at this is like kernel Gt minus U. That is why we are telling if your kernel is like E minus U, the integral equation is convolution type. That is why we are saying the integral equation is convolution type. Okay, so that is a small introduction on integral equation. Now we'll see how we can solve integral equation using Laplace transform. Integral equation using Laplace transform. So look at this question. Yx is equal to half x square minus 0 to x minus u into yu du. So this is an integral equation. This is an integral equation. Okay. Now our variable is x. So we have to find capital Yx. So that is the aim. That is the aim of solving this equation. That is the aim of solving this equation. Now, if you look at the b is a variable. So since b is a variable, it's actually a Volterra integral equation. It's a Volterra integral equation. Okay. Now, if you look at this one, if you say this is your f y t f t, and if you look at this one, actually your kernel, instead of t we have x equal to, we have x minus u. Okay, we have x minus u. So therefore, this is a convolution type. This is a convolution type, isn't it? This is a convolution type. Therefore, we can easily solve this differential equation. Right? So let's try it in a different case and try to solve this. Y equal to half x squared minus, so yx is equal to half x squared minus integration 0 to x minus u capital Y cube Okay, so now we want to solve this equation and find capital Yx. So let Laplace transform of capital Yx, because here variable is x, no problem. I'm taking it as x. Always it doesn't need to be t, equal to, I'm saying simple Ys. So now if I take Laplace transform both sides, Laplace transform of capital Yx equal to Laplace transform of half square minus Laplace transform of 0 to x 0 to x into y. So now, okay, so we have taken that Laplace transform of capital Yx is equal to Ys. Therefore, I have no problem in writing Laplace transform of capital Ys. Therefore, I can write this as simple Ys equal to half. I can take half out. So can anyone tell me what is the Laplace transform of x squared? What is the Laplace transform of x squared? Can anyone tell me? What is the Laplace transform of x squared? Can anyone answer me? What is the Laplace transform of x squared? It is actually Laplace transform of t squared. Laplace transform of t squared. So what is the Laplace transform of t squared? Here variable is
2
x.
over
That's all. Yeah, 2 factorial over s to the power 3, isn't it? Yes or no? So we have n factorial over s to the power n plus 1. So 2 factorial over s to the power n plus 1. So that is 3. Minus, can anyone tell me Laplace transform this part? This is the crucial one. Writing Laplace transform this part is the crucial one. Can anyone tell me the Laplace transform this one? So anywhere have you seen this one? Anywhere have you seen this one? 0 to x, x minus u, y u du. Anywhere have you seen this one? Yes or no? What is the Laplace transform of 0 to t ft into gt minus u into du. What is the Laplace transform of this one? Can anyone tell me what is the Laplace transform of this one? From the convolution theorem, I just discuss. What is the Laplace transform of 0 to t ft gt into du? Fs into ts, isn't it? Fs into ts. So Fs into ts is what? So here this is nothing but Fs into ts. So Fs into ts means that is actually Laplace transform of capital Ft into Laplace transform of capital Gt, isn't it? So now if you understand this, so if you just compare this with this equation, okay, so what you can do is you can take this as your Ft and you can take this as your Gt minus u. You can take x minus u as, so you can take x minus u as, so this is your x minus u, this is your capital Y2 or yx here. So it is what actually? Here your x is t actually. This is your x. So therefore this is nothing but Laplace transform of yx. It is nothing but Laplace transform of yx into Laplace transform of gt, not this one, gt. So if gt minus u is x minus u, so gt minus u is x minus u, what is your gt? Can anyone tell me? If gt minus u is x minus u, what is gt? So here t minus u, x minus u, sorry, this is x. If gx minus u is x minus u, what is gx? Can anyone tell me? If gx minus u is x, huh? X, it is simply x. Because wherever you have x minus u, you can put x. So that is equal to x. Therefore, this is actually Laplace transform of yx into Laplace transform of x. You understand? Do you understand this one?
Yes, sir.
Okay, fine. So that is nothing but Laplace transform of yx into Laplace transform of x. Therefore, this is nothing. This one is nothing, but you can say Laplace transform of, this is Laplace transform of capital YT, capital YX into Laplace transform of x, as I explained. So this is nothing but, you can simplify 1 over s cube minus this is ys into Laplace transform of x is nothing but 1 over s square. Okay, so Laplace transform of t is nothing but 1 factorial over t is s square. So if you take this out and if you bring to this side, you will have 1 plus 1 over s square ys is equal to 1 over s cube. So from this one, if you write ys is nothing but 1 over s into s square plus 1. If you simplify this one, you get this one. So s square plus 1, that will come here. And if you multiply by s, then you will have this one. So if you apply the partial fraction, this is nothing but, you can write it as s 1 over s You can say this is A over S plus ds plus C over S cat plus 1. And if you find A and B, okay, so here we are getting this one. Yeah, I think we can write it this way. So if you do the partial fraction, we are getting this one. So we want to find the Laplace transform of, if we take inverse Laplace transform of ys, this is nothing but 1 over s is 1 minus s over s squared is cos x, because here we are using s because the original equation is in x. Therefore, the inverse Laplace transform of s over s squared plus 1 is cos x. Therefore, the solution of the integral equation is yx equal to 1 minus cos x. Do you understand this? Do you understand?
Yes, sir.
Okay, fine. So here the crucial part is here. We actually, in solving this one, we are using the convolution theorem. Okay, so normally you will get a convolution type integral equation. Okay, then you will be able to use the convolution theorem to find a Laplace transform this kind of integration. Okay, so you have to identify, or you have to recognize that this integration is actually of convolution type. Is actually of convolution type. Then you can apply the convolution theorem and you can easily write the Laplace transform of this part. And you can do like earlier, and you can take ys, you can make ys subject, and then you can solve this algebraic equation for ys, and then if you take the integration, sorry, if you take the inverse Laplace transform, then you can easily find the solution. Okay, so most probably you will get integral equation type question for your examination. Okay, so not only that one, there may be partial differential equation and integral equation, or only integral equation, or OD plus integral, or whatever it is. Most probably you will get one question for this time. You will get one question from integral equation type question. Okay. So therefore, look at the convolution theorem carefully, because here we are applying the convolution theorem. Okay, so it is coming from the convolution part. Okay, then you will be able to write this one. Okay, so here the difference is here our variable is x, nothing else. Okay, nothing else. Okay, so I just stop here. Yeah, let's discuss this sort of beta function. We have 7 minutes time now, so we will discuss that also. Right. So beta function is a function like this. Okay, it's defined by this way. Okay, so we will study, if you when you study mathematical methods in your special degree in mathematics, you will study a function called beta function. Already we have studied gamma function. Can you remember when we in our first lecture we studied gamma function? So here we are going to here we are introducing the beta function. Okay, so there's a question. Apply the convolution theorem to show that this is actually application of convolution theorem. Okay, application of convolution theorem. Here, this is not a direct application, but we are learning this as a example. Okay, so now we want to show that beta function, beta m comma n. Beta function actually has two arguments, m comma n. These are positive real numbers. Then the beta function is defined this way: 0 to 1, x m minus 1 into 1 minus x to the power n minus 1. So this is the definition of beta function. Okay, so this will be given normally. This will be given. Okay, so using this definition, then you should be using this definition and convolution theorem, you should be able to show this one. Okay, let's try to show this one and finish the class. Okay, right. So beta function is defined as beta n is equal to integration 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 dx. Okay. So this is the definition. That is the definition. Now we want to show that beta m comma n. So we are trying to find beta function in terms of the gamma function. So beta m comma n is equal to gamma m into gamma n over gamma m plus 1. So this is the relationship between beta function and the gamma function. Actually, we can derive this relationship using the convolution theorem of Laplace transform. Okay, so we see how we can use the convolution theorem and find the answer, right? Okay, so for this one, consider the Laplace transform of 0 to t, 0 to t, 0 to t, okay, 0 to x, let's talk about that, 0 to x, 0 to x, x to the power m minus 1. Sorry. Let's take this as okay. Anyway, since time is nearly 5 o'clock, so I stop here. You may be tired. So the next class I will discuss. So please try this one. Okay, before I'll give an idea. Please try this one and tell me the answer in the next class. Okay. So let's try this way. So just consider Laplace transform of 0 to t, 0 to t, 0 to x, 0 to x, x to the power, sorry, u to the power m minus 1 into x minus u to the power n minus 1. Okay. So this is the convolution type. Look at here, u to the power m minus 1 into x minus u to the power n minus 1. So you can, what you can do is, you can just take this as your ft and you can take this as your g t minus, sorry, yeah. So yeah, you can take this as your fu, and this one you can take this as your fgt minus. So then, obviously, we know that this is nothing but Laplace transform of. Sorry, this is nothing but what? This is nothing but, yeah. This is nothing but Laplace transform of fx, because my variable is x. Here I am taking as x. So that is my t. Okay. So fx into Laplace transform of dx. Okay. So in that way you can try. So fx means what? Fx means this is what? Laplace transform of x to the power m minus 1 Laplace transform of gx. Actually, gt minus u is x minus u. Therefore, gx is equal to what? That is x to the power n minus 1. Okay. So using the gamma function, you can write this one. So what is this actually? This is actually gamma n over s to the power m into, sorry, gamma m. Gamma n over s to the power n. Okay, so you can write this as gamma n gamma n over s to the power n plus. Then if you take the inverse Laplace of this one, gamma m into gamma n over s to the power n plus 1, then that is nothing but this one. That is nothing but 0 to x, this one. Okay. So please try this in this way, and we'll discuss in the next class also. Okay. So thank you very much, and I stop here. If you want, I will share this writing pad with you. And you have tomorrow. I have put a real analysis class from 9 to 11. So okay, so you all will meet in the real analysis class tomorrow. So in tomorrow's class, I will start functions. Okay, I will start functions. So I stop here for today.